Hello again. It's time for another lecture, this time on section 7.6. So 7.6 is a section now where we start to talk about elimination reactions instead of just substitution reactions. And specifically, we're going to talk about E2 reactions after we go over a small set of review and talk about the types of eliminations that we can see in this chapter. So what we'll end up learning about is a lot of base-centered chemistry. And there's something that we need to remember, and that is that all of our past knowledge from organic chemistry does not go by the wayside because we need to remember some key things from Chapter 3, such as weak acids mean a strong base, that a strong acid means a weak base upon dissociation, that a stable conjugate base indicates that it came from a strong acid dissociation, and that an unstable conjugate base came from weak acid dissociation. And this really brings us to a topic that we all knew and love, which was REO. The idea that you can compare two different conjugate bases, their stability, by systematically going down the REO chart. That is, comparing the atom, the effects of resonance, the effects of induction, and the effects of the orbital that are involved in the conjugate base. Now, REO can help us determine the base strength because, as we talked about earlier, having a more stable conjugate acid meant a strong acid, and an unstable conjugate base meant a weak acid. And because we have a weak acid, we then have a strong base. So using REO, you would be looking for the unstable conjugate base so that you can find the strong base that you need for the E2 reactions, or for the elimination reactions in general. And when we say elimination reactions, really what we're talking about is systematically describing one specific type of chemical reaction, and that is a beta elimination. And we say beta elimination because we are dealing with the beta carbon, such as in this reaction here. In this reaction, you can see that we have an alkyl halide where the beta carbon has an available hydrogen, and that hydrogen can be deprotonated by a base that is also present in solution. And upon deprotonation, you end up getting the alkene product plus the protonated base and the eliminated halide anion. And in chemistry, or in organic chemistry, this is called a dehydrohalogenation. It's part of the organic chemistry as a second language type curriculum here, and it's called dehydrohalogenation because we lose a hydrogen and a halogen from the molecule, so it's dehydrohalogen. And then because it's doing something, or because something is happening to the molecule, we call that an ation. It means that some action was performed on the molecule. So you put all these things together and you get a dehydrohalogenation. Right. So the two types of reaction that we can have in terms of eliminations are either concerted one-step bimolecular elimination, which is called E2, or two-step unimolecular elimination called E1. And we'll talk about both of these, but let's start with the concerted one-step way. And this is called the E2 reaction, and it's a concerted bimolecular, just like we had for the SN2 reaction. And its mechanism looks like this, where you have alkyl halide with a hydrogen in the beta position, again, a base deprotonates the hydrogen, or the proton from the alkyl halide, and in the same step, the electrons from the CH bond flow down to make a C-C double bond while it eliminates the C halide bond here, generating the halide anion. Along with this, the alkene is generated here with the blue bond shown so that you can see where the electrons came from, as well as the protonated base. And because this is a single step process, the reaction diagram looks like this, where you have reactants going to products with one transition state and one activation energy. Because it's one step, that one step is the slowest step in our reaction. And so the rate law looks like this, where the rate is equal to the rate constant times the concentration of alkyl halide times the base. And this is really key because this shows you why we call this E2. I know the naming can get kind of confusing between SN1, SN2, E2, and E1, but what you need to know is the number in those names comes from the rate law, because this rate law, this single step reaction, is a second order rate law. And so because of that, we call it E2, because there are uh, two exponents present in the rate law. Here, the two molecules that are required to make the reaction happen, the base and the alkyl halide. So next, just like in the SN2 reactions, we want to understand how changing the substrate or the molecule that we're reacting affects the rate of an SN2 reaction. And it's fairly straightforward to understand because in an SN2 reaction, thinking about that one, we could not use tertiary alpha carbons because the nucleophile could not get to the backside of the molecule for attack. And so those types of molecules were fairly useless in SN2 reactions. However, in E2 reaction, having many carbons on the alpha position to create beta carbons here with available protons speeds up the reaction, actually. So what we find is that the reaction rate that we see for E2 reactions is exactly the opposite of reaction rates for SN2 reactions, in that primary uh, alpha carbons yield the lowest reaction rates, and tertiary alpha carbons yield the highest reaction rates. Now, in addition to E2 reactions, of course, we also have the two-step bimolecular reaction called the E1 reaction. And in this reaction, the mechanism looks like this. It's very similar to the SN1 reaction, where you first have the halide group leaving from the alkyl halide to create a carbocation intermediate. And once you generate the carbocation intermediate, then a base deprotonates the alkyl carbocation to make the product, which is the double bonded carbon-carbon material here, this alkene, as shown. So we go from reactant to intermediate to product, just like we do in the SN1 version. And so our reaction diagram reflects that. We have the reactants going to intermediates through one transition state, and then a second transition state going to products. And in both steps, these have different activation energies. And remember, because activation energy 1 is much greater than activation energy 2, the slow step in this process, the one that kinetically holds up the rest of the reaction, is going to be this one, reactant to intermediate, the one where the alkyl halide leaves, generating a carbocation intermediate. And since that's the slow step, the rate law has to only consider this reactant molecule. So the rate law, as we understand it, is equal to, we'll just write it here. The rate is equal to there we are. Get my markers here. The rate is equal to the rate constant times the concentration of the alkyl halide only. Because, again, the activation energy for this step the R to I step only involves the single molecule. And because it involves a single molecule and is first order based on the amount of exponents in the rate law, we call it E1. And that's it for section 7.6.